Good morning, folks. So hopefully everybody had a nice, enjoyable, long weekend. I feel like every day is kind of like a weekend when you're in remote learning. Um, but we are back. We are counting down the days until we're back into summer. But before we closed out this section on volume, I wanted to spend one more day kind of just running through an example. It's not necessarily anything new. It's certainly not anything more challenging. It's just again another way to kind of provide structure to something that I anticipate being a little bit of a challenge for some students to visualize. Again, we're trying to do this 3D rotation of an object on a two-dimensional piece of paper. So, volumes of revolution. I am asked to find the volume of the solid of revolution generated by rotating about the x-axis, the region under the graph y equals e to the x, from x equals -1 to x equals negative or +2. So the first thing you always want to do to just kind of jump into an example like this is you really want to understand what the shape of the region is that you're actually rotating. So you're going to want to do a quick graph. It doesn't need to be anything perfect, but you certainly want to get some sense of the region R. So this space here is my region, right? That's the actual two-dimensional plane that's then rotated around the x-axis, okay? And it's going to create kind of like a trumpet-looking object, if you can try to imagine that. And then what also helps sometimes is I draw like an arbitrary rectangle. This is going to kind of symbolize a cross section of that three-dimensional solid. And I make it a little wide so you can actually see the disk that's being formed. This is called the disk method after all. So again, taking just one slice of that and rotating it around, we get this cylindrical object, aka this disk. And it's basically a cylinder. So we want to identify the radius of it, which is, of course, from x equals or y equals 0, the x-axis, all the way up to our function, which is e to the x. The width of this, now I emphasize that the width has some value, but technically it's infinitely thin. So we're just going to call it dx, some change in x. So this gives us a good sense of what to anticipate, what the shape's looking like, and what the pieces of everything we look like or we would need. So the second part, once you have a good understanding, a good grasp of what the region is, what the graph looks like, is you want to set up your integral. Keep in mind, a cylinder has pi r squared h as the volume. Now that's one integral, or one volume of one disk. The integral adds up infinitely many of these. So for this specific example, we want the integral of pi. F of x in this case is going to be e to the x squared dx. And of course, the a and the b, if I kind of imagine that this rectangle, it's arbitrary, right? So it can be positioned anywhere in the region. So the furthest to the left, the lowest x coordinate can be positioned at is -1. The furthest to the right, or the largest x coordinate it could be positioned at, is up to 2. So those are going to be your um, limits of integration. And of course, e to the x squared is just simply e to the 2x. So this integral has some value, right? So that value represents the volume of this solid of revolution. So the last step is probably the most familiar step to us by now in calculus, is you're actually evaluating the integral. And you might have noticed if you've already dove into the homework, a lot of these integrals are pretty tame. And they're following a lot of our basic rules of integration. I think setting up the integral is really the challenge here, not the actual step of integration. So we're integrating. Pi is a constant, so I'm pulling it out to the front. It's a coefficient. Integrate e to the 2x over 2, or you could say 1/2 e to the 2x, evaluated at +2 and at -1. E to the 4th and e to the -2 are no nice numbers, so I'm going to round a bit here, and we're going to get about 85.55 cubic units. If the problem specified anything type of dimension like feet, miles, whatever, you'd want to include the appropriate, but we don't have those. So just cubic units. So today is going to be like the last reinforcement day on this section. Tomorrow I'll post the problems with the homework. I'm thinking short mini assessment, maybe 2 problems, 3 problems tops on Thursday. So please be sure to reach out with any questions you have on this objects of volume before then. Okay, good luck and reach out with questions.